Hello, in this lecture I'll answer two questions. In the first question, find out the radius of this circle. And in the second question, find out the length of this line there at AP. This equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing, we have quadrilateral ABCD that is described by this circle. We know that AC is the diameter of the circle. According to what is given in the question, chord AC is the diameter of the circle. In addition, we know that side AB of quadrilateral ABCD is equal to side BC. We also know that the perimeter of this quadrilateral ABCD is equal to 18 units. This is to say the sum of its four side lengths of this quadrilateral ABCD is equal to 18 units. This is to say AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrilateral ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we define the side lengths of quadrilateral ABCD with letters. We define the length of side AB as A. So, because of the fact that AB equals to BC, it means that BC must be also equal to units in its length. Likewise, we define the length of side AD. This side AD is B. And finally, we define the length of this side CD of this quadrilateral ABCD as C. So here we can implement rule 7 in our drawing. And please click on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB. This is the diameter of the circle, and therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So here we have in our drawing peripheral angle ABC. And AC is the diameter of the circle according to what is given in this question. Peripheral angle ABC subtend on chord AB, that is the diameter of the circle, and therefore peripheral angle ABC must be equal to 90 degrees in its size according to rule 7. Likewise, we have here, this is peripheral angle ADC that also subtends on chord AC, that is the diameter of the circle, and therefore according to rule 7, peripheral angle ADC is equal to 90 degrees in its size. So in the drawing, we have those two right triangles, the right triangle ADC and the right triangle ABC. So implement the Pythagoras theorem in each triangle. First of all, we implement the Pythagoras theorem on this right triangle, triangle ABC. Here by PT is the relation for Pythagoras theorem. So in this right triangle, according to the Pythagoras theorem, in any right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. So in the right triangle ABC, AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. If you again in this right triangle ABC, according to the Pythagoras theorem, the following equation is true. That AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. AC is the missing side, so we leave it as it is, so it is AC squared equals to AB squared. AB is 8, therefore AB squared is A squared plus BC squared. BC is also 8, so BC squared is A squared. So in total we actually found out that AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. This is according to equation 1. In the next step, we'll implement the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, in this right triangle, triangle ADC, AC squared, that is the square of the hypotenuse, equals to CD squared plus AD squared. And again, in this right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to CD squared plus AD squared. AC is the missing side, so leave it as it is. So here AC squared, that is the square of the hypotenuse, equals to CD squared. CD is C, therefore CD squared is C squared plus AD squared. AD is B, therefore AD squared is B squared. So in total, according to equation 2, we have found out that AC squared equals to C squared plus B squared, while according to equation 1, we only found out that AC squared equals to 2A squared. So we have two different equations for AC squared, so in the next step we get equation 3 that states that AC squared according to equation 1 must be equal to AC squared according to equation 2. Equation 3 states that AC squared according to equation 1 must be equal to AC squared according to equation 2. So AC squared according to equation 1 is equal to 2A squared, and it must be equal to AC squared according to equation 2. That is C squared plus B squared. So in total, according to equation 3, we have found out that 2A squared equals to C squared plus B squared. Here we divide this equation 3 by 2, and finally get that according to equation 3, A squared equals to C squared plus B squared over 2. So, as I mentioned before, It's given us the question that the perimeter of this quadrangle ABCD is equal to 18 units. That is to say, AB plus BC plus CD plus DA in total equals to 18. AB is A, BC is also A, CD is C, and DA is B. So in total, A plus A is 2A plus C plus B equals to 18. 2A plus C plus B equals to 18. According to equation 4, I should find that 2A plus B plus C equals to 18. This is according to equation 4. It is also given us the question that the area of this quadrangle ABCD is equal to 16 square units in its size. It's very easy to see that quadrangle ABCD consists of those two shapes, and therefore the area of quadrangle ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, the area of quadrangle ABCD must be equal to, in total, to the area of the first shape, that is the area of this right triangle ABC, plus the area of the second shape that it consists of, that is the area of this right triangle ACD. So I don't know if you hold that the area of quadrangle ABCD in total is equal to the area of the first shape that it consists of, this is actually the area of triangle ABC, plus the area of the second shape that it consists of, this is actually this right triangle ADC. It is given us the question. It's given us the question that the area of quadrangle ABCD is equal to 16 square units. Therefore, we substitute the area of quadrangle ABCD by 16 and get that 16 equals to the area of the right triangle ABC. What is the area of this right triangle ABC? The area of triangle ABC must be equal to the base AB times the height BC over 2. AB is A, BC is also A over 2. So in total, it's equals to A times A is A square over 2. So in total, we found out that the area of the right triangle ABC is equal to A square over 2 plus the area of the second shape that is quadrangle ABC consists of, is actually the area of this right triangle ADC. The area of the right triangle ADC equals to the base AD times the height DC over 2. AD is B, DC is C over 2. So in total, it is equals to B times C over 2. The area of the second shape, that is the area of the right triangle ABC, the area of the right triangle ADC, it is equals to B times C over 2. So in total, we should find out that according to equation 5, 16 equals to A square over 2 plus BC square times BC over 2. Here we'll multiply this equation, equation 5 by 2, and finally we get that according to equation 5, 16 times 2 is 32. So 32 equals to A square over 2 times 2 is A square, plus BC over 2. BC over 2 times 2 is BC. So in total, according to equation 5, we should find out that (32) equals to A square plus BC. Well, according to equation 4 actually, according to equation 3, we found out that A square equals to C square plus B square over 2. And again, according to equation 3, we only found out that A square equals to C square plus B square over 2. And therefore, we can substitute A square in this equation, equation 5, by c square plus b square over 2 from this equation, equation 3. So we do it now to get it according to equation 5. (32) equals to a square is c square plus b square over 2 plus bc. The total according to equation 5, I shall find out that 32 equals to c square plus b square over 2 plus bc. So here we multiply bc by 2 and then we divide it by 2 in order to account factor of this expression. And we get that according to equation 5, 32 equals to c square plus b square over 2, and here we have 2 times bc over 2. We multiply bc by 2 and then we divide it by 2, so we change nothing. It is allowable to multiply any expression by 1. So today we found out that according to equation 5, 32 equals to c square plus b square times 2 times bc over 2. So here we multiply this equation 5 by 2 and finally get that according to equation 5, 32 times 2 is 64 equals to c square plus b square plus 2 times b times c. So here we can use the algebraic identity that says that a square plus b square plus 2 times a times b is equal to a plus b square. So according to this algebraic identity, we get that here we have 64 equals to c square plus b square plus 2 times bc according to this algebraic identity will be equal to c plus b square. So total according to equation 5, we actually found out that 64 equals to c plus b square. So here we'll take out of this equation and finding that c plus b equals to the square root of 64, that is 8. So according to equation 5, c plus b equals to 8. This is according to equation 5, according to equation 4, according to equation 4, we already found out that 2a plus b plus c equals to 18. According to equation 4, we already found out that 2a plus c plus b equals to 18. But according to equation 5, c plus b equals to 8. So we can substitute c plus b in this equation 4 by 8. So we do it now, we get that according to equation 4, 2a plus c plus b, and c plus b according to equation 4 is 8, equals to 18. So here subtract 8 from this equation 4, and finally that according to equation 4, this equation 4, two a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divide this equation 4 by 2, and finally that a equals to 10 over 2, that is 5. So if you want to know that according to equation 4, A equals to 5 units in its length. And again, if you want to know that A equals to 5 units in its length. So actually, if I know that AB equals to A equals to 5, that is to say AB equals to 5. Likewise, if I know that BC is also equals to A equals to 5, that is to say BC equals to 5. So in the next step, we implement the Pythagoras theorem on this triangle ABC. The only missing side in this triangle ABC is the hypotenuse AC. So by implementing the Pythagoras theorem on this triangle ABC, we find out the length of the hypotenuse AC. Here by PT is the version for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. And again, according to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so leave this it is, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. Plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, we found out that AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 2 times 25, and get that AC squared equals to 2 times 25. So here we take a root out of this equation, and finally get that the hypotenuse that also the diameter of the circle AC equals to the square root of 25, that is 5, so inside the root we left only with 2. So the diameter AC of the circle equals to 5 times square root of 2 units in its length. According to what is given as a question, AC is the diameter of the circle, that equals to 5 times square root of 2 units in its length. And therefore, the radius of this circle must be equal to the diameter over 2. So the radius R of the circle must be equal to the diameter AC over 2. The diameter AC is 5 times square root of 2. So the diameter over 2 is 5 times square root of 2 over 2. Is equals to 3.536 units in its length. So if you found out that the answer to this question is that the radius of this circle is equal to either 5 times square root of 2 over 2 square units in its length. So in terms of numbers, the radius of this circle is equal to 3.536 units in its length. So we finish with the first question. In the next step, I'll present you the second question of this lecture. And so the second question. Our task in this second question is to find out the length of this line segment AP. This equals to x. We have to find out the value of x. So in the drawing, we have a circle this circle is described by the right triangle ABC. Or the right triangle ABC blocks this circle. Angle ABC equals to 90 degrees in size. In addition, we know that line segment QS equals to 25 units in its length. This is called QP. This equals to 24 units in its length. Again, our task is to find out the length of this line segment AP. This equals to x. So first of all, we'll implement rule 2 in our drawing. Repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing, a circle, this is the common start point, point P. For this common start point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. This is to say, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So if we can implement this rule 2 in our drawing. Why? Because in our drawing, this is the common start point, point A. For this common start point, point A, we have two tangents to this circle. Tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP equals to x. X is the variable that we are looking for in this question. But AP equals to x, and therefore AQ must be also equal to x. According to rule 2. In the next step, we will define the tangent point of tangent SC with this circle. This point is point M, or the point of tendency of tangent SC with this circle. This point is point M. And we define the length of tangent BM SA. This is to say, tangent BM equals to a units in its length. So here we can implement rule 2. Because if we focus on the common start point, point B, from the common start point, point B, we have two tangents to this circle, tangent BM and tangent BQ. Q is the point of tendency of tangent AB with this circle. So from the common start point, point B, we have tangent BQ and tangent BM. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM equals to A, therefore BQ must be also equal to A units in its length. In the next step, we'll focus on this common start point, point S. From this common start point, point S, we have tangent SM that is tangent to this circle at point M. And you also have here, this is called PQ. The extended chord PQ touches point S. Again, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. And the current point C. So I click quickly on rule 10. According to rule 10, that is true in any circle. If AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT squared equals to PA times PB, and PT squared equals to PA times PB. So, in the drawing, we have a circle. This is the common external point T. For this common external point T, we have tangent PT, that is tangent to this circle at point T. And we also have, this is called BA. This, the external chord BA touches point P. And the external chord BA touches point P. So in this drawing, the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So we mentioned before, we can implement rule 10 in our drawing because all the requirements of rule 10 are satisfied. Why? Because we have tangent SM that is tangent to this circle point M. Likewise, we have also chord PQ. The extended chord PQ touches point S. Again, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. So write it down. If we focus on the common start point S, according to rule 10, the following equation is true. And that SM squared equals to SQ times SP. And again, according to rule 10, if we focus on the common point S, the following equation is true. That SM squared, that is the square of the tangent, equals to SQ times SP. SM is the missing tangent. We don't know the length of SM, so we leave it as it is. So it is SM squared equals to SQ is 25 times SP in total equals to SQ, that is 25, plus SP, that is 24. So in total, SP equals to 25 plus 24, that is 49. And again, SP in total equals to 49. So in total, we have found out that SM squared equals to 25 plus 49. So here we'll take a root out of this equation. And finally, we get that SM, the length of tangent SM, in total it is equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. SM equals to 35 units in its length. This is tangent SM equals to 35 units in its length. What is the length of the missing line segment? Line segment SB. What is the length of this line segment SB? From the drawing, it is very easy to see that SB in total equals to SM minus BM. Again, SM minus BM equals to SB. So on and on. SB in total equals to SM minus BM. So SB equals to SM, that is 35, minus BM, that is A. So in total we should find out that SB equals to 35 minus a units in itself. Write it down, SB equals to 35 minus a units in itself. So in the next step, we will implement the Pythagoras theorem on this right. Okay. We know that SM is a tangent to the circle at point M. SM as a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of SM at point B? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So we should find out that angle SQB is the right angle. So in the next step, we implement the Pythagoras theorem on this right ring triangle, triangle QBS. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation from Pythagoras theorem. So in this right triangle SQB, the right green triangle SQB, according to the Pythagoras theorem, SQ squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. And again, according to the Pythagoras theorem, in this right triangle SQB, SQ squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. According to what is given as the question, SQ is 25, therefore SQ squared is 25 squared, that is 625, and it is equal to QB squared. QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus 8 squared. So in total, I shall find out that 625 equals to 8 squared plus 35 minus 8 squared. So here we'll open the brackets of this expression and get that 625 equals to 8 squared plus 35 minus 8 squared equals to 35 squared, that is 1225. Plus a squared, minus 2 times 35 times a is minus 70a. So that we should find out that 625 equals to a squared plus 1225 plus a squared minus 78. A squared plus a squared is 2a squared. Minus 70a plus 1225 equals to 625. So here subtract 625 from this equation. So in this side of the equation you left with nothing, that is to say 0, while on the other side of the equation we have 2a squared 178. We have 1225 from 625 is equal to 600. So in total we should find out that 0 equals to 2a squared 178 plus 600. So here we divide this equation by 2 and finally that 2a squared over 2 is a squared. 178 over 2 is 135a and 600 over 2 is 300. 0 over 2 is 0, so in total we should find out that a squared minus 35a plus 300 equals to 0. Again, I should find out that a squared minus 35a plus 300 equals to 0. So really, this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 35a plus 300, the variable that we are looking for is a. So x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 35. And finally the coefficient c equals to 300. So we have all the data from a specific quadratic equation. You just have to put the data inside this general formula for x. In this way we find out the value or the values of a, because we are looking for a. The variable that we are looking for this quadratic equation is a. So x will be equal to a. So we substitute x by a. We get that a equals to minus b. b is minus 35, therefore minus b is minus 35, that is plus 35. Plus minus square root of b squared. b is minus 35, therefore b squared is minus 35 squared, that is 1225 minus 4 times a times c. So we have minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. c is 300, so minus 4 times 300 is minus 1200. So in total, minus 4 times ac is minus 1200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we should find out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. So a in total equals to 35 plus minus 1225 minus 1200 is 25. So inside the root we left only with 25 divided by 2. The square root of 25 is 5, so in total we get that a is equals to 35 plus minus the square root of 25 is 5 over 2. So in total we should find out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40 and 40 over 2 is 20. So the first solution for A is that A equals to 20. Well, we have also the second solution for A. The second solution for A is that A equals to 35 times 5 over 2. 35 times 5 is 30 and 30 over 2 is 15. So the second solution for A is that A equals to 15. And the first solution for A is that A equals to 20 units in its length. What is A? A is the length of QB equals to A, and BM also equals to A. A is the length of those two line segments, QB and BM. But why is A is important to us? Our task was to find out the value of X. But why A is so important to us? We'll find out why it is so important to find out the value of X. So in the next step, we'll do a construction. First of all, this is triangle ABQ. The red triangle ABQ is an isosceles triangle. Why the green triangle ABQ is an isosceles triangle? Because side AQ equals to side AP, and therefore it is an isosceles triangle. QP is of course the best of the isosceles triangle, triangle AQP. So in the next step, from point A, we will go perpendicular on the base QP. Again, from point A, we will go perpendicular to the base QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point A and the base QP. This point is point Z. So in conclusion, we should have here the green isosceles triangle, triangle AQP, and we do the perpendicular AZ to the base QP. So here we can implement rule 21 in this isosceles triangle, triangle AQP. So repeat quickly on rule 21. According to rule 21, the perpendicular to the base of an isosceles triangle bisect the base. So in the drawing, triangle ABC, it is an isosceles triangle because side AB equals to side AC. From the vertex A, we do perpendicular AO to the base BC. Again, we do perpendicular AO to the base BC. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 21, the perpendicular AO to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Each half must be also equal to BC over 2 because it bisects the base. So the first half BO equals to BC over 2, and the second half also equals to BC over 2. So BO, the first half also equals to the second half, so BO equals to OC equals to BC over 2. So we can definitely implement rule 21 in our drawing. In our drawing, we have associated triangle AQP. We go perpendicular AZ to the base QP, according to Rule 21. Perpendicular AZ to the base QP bisect the base QP. That is to say, divide the base QP to two halves. Each half must be also equal to QP over 2. So the first half of Z equals to the second half ZP, and each half must be equal to QP over 2. So OZ equals to ZP equals to QP over 2. So write it down. According to Rule 21, in the associated triangle AQP, the associated triangle AQP, according to Rule 21, the perpendicular AZ to the base QP bisect the base QP. That is to say, or QZ equals to ZP equals to QP over 2. So the first half is QZ, and then it also, of course, equals to the second half, that is ZP, and each half must be equal to QP over 2. And again, the first half of the base QP equals to or QZ, this is of course equals to the second half ZP, and each half must be also equal to, of course, equals to QP over 2. QP is 24, therefore QP over 2 is 24 over 2. (24/2) is 12. On this long equation, we know that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. QZ equals to 12, ZP also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of these vertex angles, angle AQZ is alpha, then the size of this vertex angle QBS must be also equal to alpha according to the rule that I mentioned. So in this right-green triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. 90 degrees plus 90 degrees, it is equal to 180 degrees. This is the sum of the angles in any triangle. Likewise, in this green triangle QSB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay, It is very easy to see from the drawing that the right green triangle AQZ is similar to this right green triangle SQB. So what those two green right triangles are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the triangles of this right green triangle SQB are corresponding equal to all the triangles of this right triangle AQZ, and therefore those two right green triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the right green triangle SQB is similar. This is the sign of similar to this right green triangle AQZ. According to angle similarity rule. But again, if you found out that the right green triangle SQB is similar to the right triangle AQZ according to angle similarity rule. And for the fact that those two right green triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side SQ of this green right triangle SQB over side AQ of this green right triangle AQZ is equal to side QB of this green right triangle SQB over side QZ of this green right triangle AQZ. So write it down. Repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle SQB of side AQ of the right triangle AQZ equals to side QB of the right triangle SQB or side QZ of the right triangle AQZ. SQ equals to 25. Over AQ. AQ equals to X. That is the variable that we are looking for this question. And it equals to QB. QB equals to A. Now we'll find out why A is so important to us. QB equals to A over QZ. QZ equals to 12. And further, we should find out that 25 over X equals to A over 12. So here we will cross multiply this equation. And we get that 25 times 12 equals to X times A. 25 times 12 is 300. So in total we should find out that 300 equals to X times A. Now it is very clear why A is so important to us. Note that A equals to either to 20 or 15. So we can substitute A by 15 or 20, and X will be equal to 300 over 15 or 300 over 20. So by finding the value of A, we'll find out the value of X, that is the variable that we are looking to in this question. That is the variable that we are looking for in this question. For that reason, A is so important to us. Okay, so here we divide this equation by A, and find out that X equals to 300 over A. So we have to find out what is the real value of A, because we have two solutions for A. A could be equal to 20 or A could be equal to 15. This is the solution of the quadratic equation. In order to find out the real value of A, I copied this rectangle ABC with the circle that is inscribed by this rectangle ABC in a new page, and realize this triangle with the circle in order to find out what is the real value of A. Is it equals to 20 or 15? Okay. So this is the rectangle ABC that I copied from the original drawing. This is the original circle that I copied. So here we already found out that QB equals to A. AQ of course equals to X according to what we already found out. Point M is the point of tendency of tangent BC with this circle. In the next step, we define the center of this circle. This point is point O. And we join points O and M together by a straight line. We define the radius of this circle as R. And we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle. This is equals to R according to our definition. The radius OM, that is equals to R, the radius OM is down to point M, that is the point of tendency of tangent BC with this circle. And whenever your radius is down to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, point Q is the point of tendency of tangent AB with this circle. In the next step, we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in this small quadrilateral OQBM, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in size according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral QOMB is 4 rectangles, and therefore can relate to quadrilateral OMB is a rectangle, although the square to it is a rectangle. It is enough for us to look at quadrilateral QOMB as a rectangle. We don't need any more. So we write to quadrilateral QOMB is a rectangle. So the small quadrilateral QOMB is a rectangle because it has 4 rectangles. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle QOMB, side OM equals to the opposite side QB. But OM is R, therefore the opposite side QM must be also equal to R units in its length. So in total we should find out that QB equals to A and it also equals to R. In the next step, we will do a construction, that is to say, we will extend the radius MO by a straight line until it touches the circle. And we will define the touching point of the extended radius MO with this circle. This point is point Z. MO is the radius of the circle, it is absolutely a straight line. We will extend the straight line MO by a straight line. The result MZ must be also a straight line. So if we focus on the right side of the straight line MZ at point O, here the sum of the areas must be equal to 180 degrees according to rule 3. So which areas we have at the right side of ZM at point O? We have this angle that is the right angle plus this missing angle. Total must those two areas. The sum of those two areas must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of this circle, equals to R. ZM is a chord that passes through the center of the circle, and therefore it is the diameter of the circle. It is not relevant to the question, but MZ is the diameter of the circle, So in the next step, we will do a construction, that is to say, we will do a tangent to the circle at point Z. Again, from A and B, we will do a tangent to the circle that will be a tangent to the circle at point Z. The tangent will be tangent to the circle at point Z. When you find the touching point of this tangent with this circle, this point is point C. I repeat again that TZ is a tangent to this circle at point Z according to our construction. The radius OZ that equals to R, the radius OZ is drawn to point Z, that is the point of tendency of TZ with this circle. And whenever your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius Z0. If TZ is perpendicular to Z0, it means that this angle equals to 90 degrees according to rule 1. So inside the upper quadrilateral TZ or Q, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees inside, and therefore quadrilateral TZ or Q that has 4 rectangles, it is a rectangle, although it is square related to quadrilateral TZ or Q is rectangle. We don't need more. So in the upper rectangle Q, T, Q, or Z, the opposite sides are equal to each other. So side ZO is equal to side TQ. But ZO is R, it is the radius of the circle, therefore TQ must be also equal to R. We actually found out that line segment QB equals to A and A equals to R. So write it down. Line segment QB equals to A and line segment QB also equals to R. What is line segment AQ equals to X. Line segment AQ equals to X. Line segment AQ also equals to AT plus TQ. So line segment AQ equals to AT plus TQ. TQ is R, so in total line segment AQ equals to AT plus R. Line segment AQ equals to AT plus R. Line segment AQ equals to AT plus R, and of course line segment AQ equals to X. AQ equals to X. AQ equals to X. So here AT plus R, it is definitely greater than R. Again, AT plus R, it is definitely greater than R because AT is a positive number. Again, AT is a positive number, therefore AT plus R must be greater than R. So you can write here that AT plus R is greater than R because AT is a positive number. And from this law inequality, we derive that X is greater than R. Again, from this law inequality, A equals to QB equals to R is less than AT plus R equals to AQ equals to X. We derive that X is greater than A. X is greater than A. It will help us, this inequality will help us to find out which is the right length of A, whether if it is 20 or 15. We find out what is the real length of A by this inequality that X is greater than A. So just find out that X is greater than A. So A could be equal to either to 20 or to 15. A equals to 20 or A could be also equals to 15. We have two solutions for A. We already found out that X equals to 300 over A. So I can write there that X equals to 300 over A. if a equals to 15, it means that x equals to if a equals to 15, it means that x equals to 300 over 15, that is 20. But again, we should hold on that if a equals to 15, then x must be equal to 20. Likewise, if a equals to 20, then x equals to 300 over 20, that is 15. Repeat again, we should hold on that if a equals to 20, then x must be equal to 15. So x equals to 15 is definitely, 15 is definitely less than 20. That equals to a. From this inequality, we know that x is less than a. Yes, it's smaller than a. Okay. X is smaller than a. Contradicts to our findings that x must be greater than a. So due to this contradiction, when you cancel the solution, a cannot be equal to 20. The solution is the correct solution. And then focus on only this solution. That if a equals to 15, then x equals to 20. So x equals to 20. And 20 is definitely less than 15. That equals to a. It equals to a. And from this inequality, we derive that x is less than a. Again, x that is equal to 20 is greater than 15, of course. 20 is greater than 15. This equals to a. Again, x is equal to 20 is greater than 15. 20 is greater than 15. And 15 equals to a. And from this inequality, x equals to 20 is greater than 15 equals to a. We will derive that x is greater than a. Okay. So x is greater than a. Exactly according to our findings that x must be greater than a. So it doesn't contradict our previous finding that x must be greater than a. X must be greater than a. So the final answer to the question is that x equals to 20 units in its length. So line side AP is equals to x is equal to 20 units in its length. It again, I should download it. The length of this line segment AP is equals to x is equal to 20 units. Again, AP is equals to x is equal to 20 units in its length. And that is the answer to the question. So we finished to answer on the second question. So in the next step, I will summarize the lecture. We'll start with the first question, of course. Our test in this first question is to find out the radius of this circle R. This circle blocks quadrilateral ABCD, or quadrilateral ABCD is inscribed by this circle. It is given us the question that AC is the diameter of this circle. Side AB of quadrilateral ABCD is equal to side BC. In addition, we know that the perimeter of this quadrilateral ABCD is equal to 18. That is to say, the sum of the four side lengths of quadrilateral ABCD is equal to 18. That is to say, AB plus BC plus CD plus DA equals to 18 in total. And it is also given us in the question that the area of this quadrilateral ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we define the side lengths of this quadrilateral ABCD with letters. We define the length of side AB as A. And because of the fact that side AB equals to side BC in its length, it means that BC must be also equal to units in its length. Likewise, we define the length of side AD as B. And we define the length of side CD as C. In the next step, we implemented Rule 7 in our drawing. Repeat quickly Rule 7. According to Rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of the circle, and therefore according to this Rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to this Rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So we can implement Rule 7 in our drawing. Why? Because in our drawing, we have, this is the peripheral angle ABC that subtends on chord AC, that is the diameter of the circle according to what is given us in the question, and therefore according to Rule 7, peripheral angle ABC must be equal to 90 degrees in its size. Likewise, this is peripheral angle CADC that also subtends on chord AC, that is the diameter of the circle, and therefore according to Rule 7, peripheral angle ADC must be equal to 90 degrees in its size. So, in the drawing, we have those two right angles, right angle ABC, this is right angle ADC. So in the next step, we implemented the Pythagoras theorem on those two right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right angle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Repeat again, right angle ABC according to the Pythagoras theorem. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so leave it as it is. So it is equals to, so it is AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So we found out that AC squared in total equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared according to this equation, equation 1. In the next step, we implement the Pythagoras theorem on this right angle, triangle ADC. In this right angle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. Okay, again, this right angle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, must be equal to CD squared plus AD squared. AC is the missing side, so leave it as it is. So it is AC squared equals to CD squared. CD is C, therefore CD squared is C squared plus DA squared. DA is B, therefore DA squared is B squared. So in total, we found out that AC squared, that is the square of the hypotenuse, equals to CB squared plus AC squared equals to C squared plus BC squared. So we have two different equations for AC squared. AC squared either equals to 2A squared, or AC squared equals to c squared plus b squared. Therefore, we created equation 3 that says that ac squared according to equation 1 must be equal to ac squared according to equation 2. Put again, according to equation 3. AC squared according to equation 1 must be equal to AC squared according to equation 2. So AC squared according to equation 1 is 2A squared, and must be equal to AC squared according to equation 2. AC squared according to equation 2 equals to C squared plus B squared. So in total according to equation 3, we found out that 2A squared equals to C squared plus B squared. Here we divided this equation 3 by 2, and finally found out that A squared equals to C squared plus B squared over 2. This is according to equation 3. According to what is given as the question, the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and AD is B. So in total, A plus A is 2A, so 2A plus C plus B equals to 18. According to equation 4, we should find out that 2A plus B plus C equals to 18. In addition, it is given us the question that this is quadrilateral ABCD that is equal to 16 squares in size. But quadrilateral ABCD consists of those two shapes, and therefore quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of this first shape, that is the area of this right triangle ABC, plus the area of this second shape, that is the area of this right triangle ADC. Okay, again, the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the right triangle ABC, plus the area of the second shape, that is the right triangle ADC. It is given as a question that the area of quadrilateral ABCD equals to 16 square units inside, therefore substitute the area of quadrilateral ABCD by 16, and it is equal to the area of the right triangle ABC. What is the area of this right triangle ABC? The area of this right triangle ABC, it is equal to the base AB times the height BC over 2. AB is A, BC is A, divided by 2. So it is in total 8 times 8 times 2, 8 times A over 2. That is to say, it is A squared over 2. So in total, the area of the right triangle ABC equals to A squared over 2 square units in size, plus the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the ADC over 2. AD is B, BC is C, divided by 2. So it is in total B times C over 2. The area of the second shape, that is the area of the right triangle ADC equals to B times C over 2. So in total, according to equation 5, we actually found out that 16 equals to A squared over 2 plus BC over 2. So here we multiply this equation 5 by 2, and finally found out that 16 times 2 is 32 equals to A squared over 2 is A squared plus BC squared over 2 is BC. So in total, we should find out that 32 equals to A squared plus BC. And then we should find out that according to equation 5, 32 equals to A squared plus BC. According to equation 3, we only found out that A squared equals to C squared plus B squared over 2. Again, A squared equals to C squared plus B squared over 2. So we can substitute A squared in this equation 5 by C squared plus B squared over 2 for this equation 3. We did it, and we found out that 32 equals to A squared is C squared plus B squared over 2 plus BC. So here we multiplied BC by 2, and then we divided by 2 in order to overcome a factor of this expression. In total, we actually found out that according to equation 5, 32 equals to C squared plus B squared over 2. We have 2 times BC over 2. So here plus 2 times BC over 2. We multiplied by 2 and then we divided by 2, so we change nothing. So in total, according to equation 5, we actually found out that 32 equals to C squared plus B squared plus 2 times BC over 2. So here we multiplied this equation 5 by 2, and finally found out that 32 times 2 is 64 equals to C squared plus B squared plus 2 times BC. Yeah. According to equation 5, we should find out that 64 equals to c squared plus b squared plus 2 times b times c. We have the algebraic identity. It says that a squared plus b squared plus 2 times ab equals to a plus b squared. Therefore, according to this algebraic identity, we get that c squared plus b squared plus 2 times bc will be equal to c plus b squared. So 64 equals to c plus b squared. Here we took out all of this equation in question 5, and I should found out that the square root of 64 is 8, and the square root of cb squared is c plus b. So in total, c, according to equation 5, c plus b equals to 8. According to equation 4, we only found out that 2a equals to 2a plus c plus b equals to 18. Repeat again. According to equation 4, we found out that 2a plus b plus c equals to 18. So I copy this equation 4 here. 2a plus c plus b equals to 18. But c plus b equals to 8 according to equation 5. So we can substitute c plus b in this equation 4 by 8. We did it, and we found out that 2a, c plus b is 8 equals to 18. So according to equation 4, 2a plus 8 equals to 18. Here we subtracted 8 from this equation, and we found out that 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divided this equation 4 by 2, and we found out that a equals to 10 over 2, that is 5. So then we found out that according to equation 4, a equals to 5 units in itself. That is to say, this is side AB of one another ABCD that equals to A, and A equals to 5. So AB equals to 5. Likewise, BC equals to A, and A equals to 5, and therefore BC also equals to 5. So in the next step, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in this right triangle ABC, AC squared equals to AB squared plus BC squared. Okay, again, the right triangle ABC according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC is the missing side, so it is AC, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total we should find out that AC squared equals to 25 plus 25. 25 plus 25 is 50, so AC squared equals to 50. Here we substitute 50 by 2 times 25, so in total we should find out that AC squared equals to 2 times 25. Here we took out of this equation and we found out that AC equals to the square root of 25, that is 5, so inside the root we left only with 2. So in total we should find out that the diameter AC of the circle equals to 5 times square root of 2. Therefore, the radius must be equal to half of the diameter. That is to say, the radius of the circle, that is the radius that we are looking for, must be equal to the diameter AC over 2. But AC is 5 times square root of 2. Therefore, the radius must be equal to 5 times square root of 2 over 2. In terms of numbers, the radius R equals to 3.536 units in itself. Okay, again, we found out that the radius R of this circle, that is the radius that we are looking for in this question, is equal to either 5 times square root of 2 over 2 units in itself. In terms of numbers, the radius R of this circle is equal to 3.536 units in itself. So we finished to repeat on the first question. In the next step, repeat on the second question on this lecture. In this second question, our test is to find out the length of line segment AP. This is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is described by this right triangle ABC. So the right triangle ABC blocks this circle. In addition, we know that line segment SQ equals to 25 units in its length. This is called QP, that is equals to 24 units in its length. This is the angle ABC, this is the right angle. This is the standard SM, that is standard to the second point M. Again, our task is to find out the length of this line segment AP, that is equals to x. We have to find out the value of x. So first of all, we implemented rule 2 in our drawing. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents to the circle, tangent PA and tangent PP. And according to this rule 2, they are equal to each other. That is to say, the length of tangent PA equals to the length of tangent PB, or P equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ, but AP equals to X. X is the variable that we are looking for in this question. So, but AP equals to X, therefore AQ must be also equal to X, according to rule 2. We define the point of tendency of this tangent with this circle. We've defined the point of tendency of tangent SA with this circle. This point is point M. We define the length of tangent BM SA. And then we focus on this common standpoint, point B. From this common standpoint, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. This is to say, BM equals to BQ. But BM is A, therefore BQ must be also equal to A. In the next step, we focus on this common standpoint, point S. From this common standpoint, why point S is the common standpoint? Because in relation to this circle, it is a common standpoint because of the fact that point S is not located inside the circle, nor on the circle itself, therefore it is located outside the circle. Therefore, it is defined as an external point, and it is from point S we have tangent SM and this line segment SQ, therefore it is also a common point. So the point S is a common standpoint. From the common standpoint, point S, tangent SM, that is tangent to this circle is point M. Likewise, we have this is called PQ. The extended called PQ touches the circle. The extended called PQ touches point S. Yeah, touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, in any circle, rule 10 is true in any circle. So if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, you have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have tangent PT, this is tangent to this circle, point T. And we also have, this is called BA. The extended called BA touches point P. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can actually implement rule 10 in our drawing. Well, in our drawing, we have the common standpoint, point S. From the common standpoint, point S, we have tangent SM, that is tangent to this circle, is point M. Likewise, the extended called PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that SM square equals to SQ times SP. Again, SM square equals to SQ times SP. And again, if we focus on the common standpoint, point S, according to rule 10, the following equation is true. That Sm squared equals to Sq times Sp. Tangent Sm is the missing tangent, so we know it is. And Sm squared equals to Sq, that is 25, times Sp. Sp in total equals to Sq, that is 25, plus Qp, that is 24. So in total, Sp equals to 25 plus 24, that is 49. And again, Sq equals to 25 and Sp equals to 49. So in total, according to 10, we found out that Sm squared equals to 25 plus 49. So here we took out all of this equation and found out that Sm equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, Sm equals to 5 times 7, that is 35. The length of tangent Sm is 35 units. What is the length of this? This is 97 Sb. Sb equals to Sm minus Bm. Again, Sb equals to Sm minus Bm. So Sb in total equals to Sm, that is 30. Sm, that is 35, minus Bm, that is 8. So in total, Sb equals to 35 minus 7 units in its length. Sm is a tangent to this circle with point M. So Sm is a tangent, it is absolutely a straight line. So Sm is a straight line, so if you focus on the upper side of this straight line, Sm is point B, the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of Sm at point B? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees inside. Therefore, the green triangle SQB is a right triangle. So in the next step, we implemented the Pythagoras theorem on this green right triangle SQB. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, SQ squared, that is the square of the hypotenuse, must be equal to QB squared plus BS squared. And again, according to the Pythagoras theorem, in the right green triangle SQB, SQ squared, that is the square of the hypotenuse, must be equal to QB squared plus SB squared. SQ is 25, therefore SQ squared is 25 squared, that is 625, and it is equals to QB squared. QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 minus 8, therefore SB squared equals to 35 minus 8 squared. So in total, we should find out that 625 equals to 8 squared plus 35 minus 8 squared. So here we open the brackets of this expression and finally found out that 625 equals to 8 squared plus 35 minus 8 squared. 35 minus 8 squared equals to 35 squared, that is 1225 plus 8 squared. Minus 2 times 35 times 8 is minus 78. So 8 squared plus 8 squared is 2a squared, and we have here minus 78 plus 225 equals to 625. So here we subtract 625 from this equation. So in this side of the equation we have nothing, that is to say 0. While on the other side of the equation we have 2a squared, 178 plus 1225. 1225 plus 625 equals to 600. So in total we should find out that 2a squared minus 78 plus 600 equals to 0. Here we divided this equation by 2 and we found out that 2a squared over 2 is a squared, minus 78 over 2 is minus 45a, and 600 over 2 is 300 equals to 0 over 2 is 0. So in total we should find out that a squared minus 35a plus 300 equals to 0. And again we should find out that a squared minus 35a plus 300 equals to 0. So actually, this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus 3 plus minus square root of b squared minus 4 times ac over 2a. another specific quadratic equation, that is to say a squared minus 35a plus 300 equals to 0, the variable that we are looking for is a. So x equals to a. The coefficient a equals to 1, the coefficient b equals to 145, and the coefficient c equals to 300. So we have all the data that is needed for our specific quadratic equation in order to find out the variable that we are looking for, that is a. The only thing that is left to do is to put the data in this general equation for x. In this way we find out the value of the values of a, because a is the variable that we are looking for, and therefore x equals to a. So we put the data inside this equation, general equation, x equals to a, so we substitute x by a, and it equals to minus b. B equals to minus 35, therefore minus b is minus 35, that is plus 35, and it equals to the square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. A is 1, so minus 4 times a is minus 4 times 1, that is 4, times c is 300. So minus 4 times 300 is minus 1200, so in total minus 4 AC is minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should find out that a equals to plus 35 plus minus square root of 1225 minus 1200 over 2. 1225 minus 1200 is 25, so inside those we left only 25. So in total we should find out that a equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5, so in total we should find out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20 units in its length. And the second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is that a equals to 15, and the first solution for a is that a equals to 20. Okay, so in the next step we did the construction. This is the rectangle AQP. The rectangle AQP is an associated triangle because AQ side AQ equals to side AP. QP is of course the base of this associated triangle, triangle AQP. So we did the construction in this associated triangle, triangle AQP. That is to say, from the vertex A, we do perpendicular on the base QP. Again, from the vertex A, we do perpendicular on the base QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So in conclusion, actually draw perpendicular AZ to the base QP of the green associated triangle, triangle AQP. So therefore we can implement rule 21. So implement rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. This is triangle ABC. This is an associated triangle because side AB equals to side AC. So this triangle ABC, we did the construction, that is to say, we do the perpendicular AO to the base BC. Again, we do the perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 21, according to this rule 21, the perpendicular AO bisects chord BC. Again, the perpendicular AO bisects chord BC, or the associated triangle ABC. That is to say, it divides the base BC into two halves. The first half BO equals to BC over 2, and the second half OC also equals to BC over 2. In total, BO equals to OC equals to BC over 2. So we can actually implement rule 21 in our drawing. We have the perpendicular AZ to the base QP of the associated triangle, triangle AQP. According to Rule 21, the perpendicular AZ of the base QP bisects the base QP. That is to say, it divides the base QP into two halves. Each half, of course, equals to QP over 2. So the first half QZ equals to QP over 2, and the second half ZP also equals to QP over 2. Okay, again, we have in the associated triangle AQP, according to Rule 21, the perpendicular OZ bisects the base QP into two halves. The first half OZ, of course, equals to the second half ZP. Each half equals to QP over 2. QP is 24, 24 over 2 is 12. So from this equation, OZ equals to ZP equals to QP over 2 equals to 24 over 2 equals to 12. We derive that QZ equals to ZP equals to 12. QZ equals to 12, ZP also equals to 12. So here, those two angles are defined as vertex angles, and you know that vertex angles are equal to each other. So if you define this vertex angle as alpha, then this vertex angle must also equal to alpha because they are equal to each other. So in this right triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this green right triangle QBS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. This is the green right triangle QBS that is similar to this right triangle AQZ. So all those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we shall find out that all the figures of this green right triangle HQB are correspondingly equal to all the figures of this green right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity rule. So if you again, we shall find out that the green right triangle SQB is similar to the sign of similar to the green right triangle AQZ according to angle similarity rule. And from the fact that those two right green triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side SQ of this green right triangle SQB or side AQ of this green right triangle AQZ is equal to side QB of this green right triangle SQB or side QZ of this green right triangle AQZ. Repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle SQB or side OA of the right triangle AQZ is equal to side QB of the right triangle SQB or side QZ of the right triangle AQZ. SQ is 25, AQ is X, QB is A, and QZ is 12. So in total, we should find out that 25 over X equals to A over 12. Here, of course, multiply this equation, and we find out that 25 times 12 equals to A times X. 25 times 12 is 300, so 300 equals to X times A. Here we divided this equation by A, and we found out that X equals to 300 over A. We should find out that A qubit equals to A and B also equals to A could be equal to either 15 or 20. In the next step, we have to find out what is the correct answer for the value of A. Is A equals to 15 or 20? In order to find out what is the real value of A, I copied this triangle with the circle that is described inside it. In the page, I analyze this triangle with the circle in order to find out the real value of A. So this is the right triangle ABC with the circle that is inscribed inside it, and the point from the original drawing. We already found out that QB equals to A. Point M is the point of tendency with this circle. In addition, we know that AQ equals to X. Here, EQ equals to X and QB equals to A, according to what we already found out. In the next step, we define the center of this circle. This point is point O. We define the radius of this circle as R, and we join points O and M together by a straight line. Point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle, that is equals to R. The radius OM that is equals to R, the radius OM is 1 to point M, that is the point of tendency BC with this circle. And whenever you have radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius MO according to Rule 1. If BC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. So, point Q is the point of tendency of tangent AB with this circle. So the next step, we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equals to 1, and according to Rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. In the next step, we did the construction, that is to say we extended the radius OM that is equals to R by a straight line until it touches the circle. We define the touching point of the extended radius OM with this circle. This point is point Z. OM is a radius. A radius is definitely a straight line. When we extend the straight line OM by straight line, the result MZ must be also a straight line. So if we focus on the right side of the straight line MZ at point O, here the sum of the areas must be equal to 180 degrees. According to Rule 3, the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the right side of the straight line MZ at point O, we have this angle that is right angle, plus this missing angle. In total, the sum of those two areas must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the next step, we did another construction. That is to say, from side AB, we draw a tangent to the circle in such a way that it will be tangent to this circle at point Z. Again, we draw a tangent to this circle in such a way, from AB, in such a way that the tangent will be tangent to this circle at point Z. We define the touching point of the tangent with AB. This point is point T. Again, TZ is the tangent to point Z. TZ is the tangent to this to the circle at point Z, according to our construction. So we have tangent TZ, that is the tangent to the circle at point Z. The radius OZ is equals to R. The radius OZ is 1 to point Z, that is the point of tendency of tangent TZ with this circle. Whenever your radius is 1 to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to Rule 1. So in total, in the upper quadrant TZOQ, we have 1, 2, 3 angles. This angle equals to 90 degrees according to Rule 3. So we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees inside. Quadrant TZOQ is 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle TZOQ, side ZO must be equal to the opposite side DQ, but ZO is R, therefore the opposite side DQ must be also equal to R units in its length. So we already found out that QB equals to A and A equals to R. So I copy this equation here. We already found out that QB equals to A and A equals to R. Again, QB equals to A and QB also equals to R. Again, QB equals to A and QB equals to R. AQ equals to AT plus CQ. So AQ in total equals to AT plus CQ. TQ was R, so AQ in total equals to AT plus R. But AQ also equals to X. So AQ equals to AT plus R. From one side, AQ equals to AT plus R. But from the other side, AQ also equals to X. Again, AQ from one side equals to AT plus R, but from the other side, AQ equals to X. Here we have 80 plus r, it is definitely greater than r because 80 is a positive number. Repeat again, 80 is a positive number because it is a length, and therefore it is definitely 80 is a positive number, and therefore r plus 80 must be greater than r. And 80 plus r must be greater than r because 80 is a positive number, and from this long inequality, a equals to q, b equals to r is less than 80 plus r equals to aq equals to x. From this long inequality, we derive that x is greater than a. Okay, x is greater than a. So we just found out that x is greater than a. We have two solutions that are possible for a. A could be equal to either to 20 or to 15. We already found out that x equals to 300 over a. So we can write here that x equals to 300 over a. If a equals to 15, it means that x equals to 300 over 15, that is 20. So if a equals to 15, then x must be equal to 20. Likewise, if a equals to 20, then x must be equal to 300 over 20, that is 15. So if a equals to 20, then x must be equal to 15. So x equals to 15. 15 is definitely less than 20. So 20 equals to a. Yeah, 20 equals to a. 20 equals to a. And from this inequality, x equals to 15 is less than 20, this equals to s. To x equals to 15 is less than 20, this equals to a. From this inequality, we will derive that x is less than a. X is less than a. It contradicts the fact that we already found out that x must be greater than a. Due to this contradiction, we cancel the solution, and we're left only with the only solution, the second solution that is possible for a, that a equals to 15. A equals to 15, so then x equals to 20. So x equals to 20. 20 is definitely greater than 15. This equals to a again. 20 is definitely greater than 15. This equals to a. From this inequality, we derive that x is greater than a. Exactly like we already found out that x must be greater than a. So the other solution that x equals to 15. That equals to 15 doesn't contradict our previous finding that x must be greater than a, and therefore the solution to the question is that x equals to 20 units in its length. AP that equals to x is equal to 20 units in its length. Okay, again I should found out that the length from this line segment AP that equals to x is equal to 20 units in its length. Okay, thank you very much.